So I am going to have three talks. So basically today I will start just from like introductory things, like my own results are there more in lambda trees. But okay, so group setting on trees. Now let me do it this way. So this result is sort of a folklore that a group G is a free group if and only if it acts freely by automorphisms on a tree. So when I'm talking about action on a tree, like, okay, so first of all, what is a tree? A tree is a graph without loops, right? Without loops, it's a tree. Connected graph without loops is a tree. And to act on a tree, the group acts on a tree by automorphisms. So vertices are taken to vertices bijectively, right? And corresponding edges are taken to corresponding edges. Now, we say that the action is free if there are no inversion on edges, like it does not flip, like it does not move, like the edge AB does not move it into, like, so this is an inversion. If B becomes phi of A and A becomes phi of B, so no inversion on edges, and stabilizers of vertices, so elements which like for each vertex, the stabilizer of this vertex is trivial. So this is a free action. Now, in one direction, this is easy, right? A free group acts on its Cayley graph, right? Now, if somebody does not remember, let me recall that Cayley graph, so vertices of the Cayley graph are elements of the group, vertices of the Cayley graph are elements of the group, and we fix some set of generators. Let's say, suppose it's generated by the set A with some relations, and for every generator, the vertex G is connected to GA by an H labeled by A, and for any A in A, and like if we read it in the opposite way, so then we read A inverse. So now if, for example, if you have a free group on two generators, somehow my screen, my iPad became small. Let me just maybe, just 1 minute, let me just try to open it again. No, still small. Okay, like for example, if we have a free group on two generators and the Cayley graph, so we have identities, and we have like A, B, then A, B, and so on. So like we have a tree with like each vertex has valency 4, like here we have 2, and this is an infinite tree. So basically the Cayley graph, so this is a Cayley graph of F. The Cayley graph of a free group is a tree, because if we had a loop, then this would mean that we have a relation, then the label of the loop would correspond to the trivial element in the group. So a free group acts on a tree, like on, for example, it acts on its own Cayley graph. It is like harder to show that if a group acts freely on a tree, then it is indeed a free group. And this theorem, like it appeared in the book by Sir Trees, but I know that Latsi Babai had a result like this, had it before, and actually it goes even like even earlier. So it was like like a folklore result, but Searle and then Hyman Bass, who like they wrote a book together, they actually developed like the Bass-Searle theory, which kind of describes the structure of groups acting on trees, and the theorem would follow from the Bass-Searle theory. And I am going to talk about Bass-Searle theory today. At least I'll start. Like it was like basically Searle developed this to show that SL2Z splits as an amalgamated product, and to show that SL3Z and for larger n does not. And I'll try to talk about this also. And also another subject of these lectures. So I'm not only going to talk about like this was a simplicial tree. And I also going to talk about R trees and in general lambda trees. Now, R trees, what is an R tree? It is, one can think about R tree as about zero hyperbolic metric space. So it is a metric space. R stays for real numbers. It is a metric space which satisfies the following properties. So it is a geodesic metric space. So for any two elements, there is a geodesic. So since it is a metric space, we know the distance between the elements. And so for any two elements, there is a path of length equal to the distance between these elements. Now, if two segments intersect in a single point, which is endpoint of both, then their union is a segment. So like, for example, if we have, so this is a segment, and then there is another segment, and they intersect in a single point, and it is the endpoint of both of them, then their union is also a segment. So if this is geodesic between, let's say, A and B, and this is geodesic between B and C, then the union is a geodesic between A and C. So it's like a tree-like property, like we have in the trees. Also, the intersection of two segments with a common endpoint is also a segment. Like if we have something like this, so then the intersection, like there is a segment AB and BC, then this BD, like we go A to B, we go B to C, then BD is also a segment. It's also geodesic. So again, like one can think, if you know what is a hyperbolic metric space, one can think about R3 as a zero hyperbolic metric space. Like geodesic triangles, basically, like if you have a geodesic triangle between A, B, and C in this space, then they are tripods. Like geodesic triangles are tripods. Now let me give you examples of R3s. First of all, the real line is an R3. Like we just think about real line, and like every 2 points are vertices of a real tree. And the distance between the metric, it is just the distance on these points, between these points along the real line. Then also a geometric realization of a simplicial tree. What I mean here, like if you draw let's draw a simplicial tree. And like if you talk about simplicial tree or like normal tree, then the vertices, these are vertices, right? We have vertices and edges. And geometric realization is just a picture of the tree. Like, and then here, like when we talk about R3, like any two points on this picture are considered as vertices of an R3. And like, for example, we can think that each edge has length 1, then the distance between these 2 points, it is just the distance computed along the realization. So it is also an R3. Then something more interesting, for example, we can turn a plane into an R3. Like take R2 and define metric like this. So if you need to go from like the distance from point x1, y1 to the point x2, y2, computed like this. We go to the x-axis, then we go along the x-axis, and then we go again orthogonally. So this is a geodesic. And then like if they are on the same vertical, if 2 points are on the same vertical line orthogonal to the x-axis, then we go along this line. Then the distance, the geodesic goes along this line. And so then this looks like some very, very dense hairbrush, right? Because all this are geodesics, and like these things are geodesics. Another example, it's move this. It's again like a plane, what is called like French railway system metric. I mean, this is like probably you can think about the distance, how it's defined. Basically, it's defined like this. So there is a Paris in the middle, and railway system looks like this. We have rays going from Paris, right? So if you want to come from A to B, and they are on different rays going from Paris, you take a train to Paris, and then you take a train from Paris to B. Now, if your points, or like your towns happened to be on the same ray, then this would be a geodesic between them. Otherwise, you have to go like this. This is a geodesic. So you go to the origin, along the straight line to the origin, and then you go to point B from the origin. So that's another example of an R3. Like I'll talk later, like why R3s are important. So today I'd like to talk about bus search theory. So bus search theory. So we're going to have groups acting on simplicial trees, ordinary trees by automorphisms. So like, and let's begin with some constructions, some group theoretic constructions, because they're important in this business. I don't know, just tell me if you know all this, because like it's maybe I'm going to talk about something obvious. So first, let me define an amalgamated free product. So suppose we have 3 groups, A, B, and C, and suppose we have injective homomorphisms, sigma and tau from C to A and B. Now, if this diagram is a push out, then we write that G is an amalgamated amalgamated free product of A and B over C. Now, push out means that if we have some other group, G prime, and we have the diagram like this, then there is a unique homomorphism from G to G prime. So it's like coproduct property of G. It has a universal property that if there is some other group, G prime, such that we can have this diagram, then there is a unique homomorphism from G to G prime. Now, in terms of generators and relations, things look like this. So if A is given by generators S1 and relators R1, and B is given by generators S2 and relators R2, then, okay, so then amalgamated free product is given by the union of generators of A and B. And then we have relations of A, relations of B. And then we say that sigma of C equals to tau of C. Like remember that sigma and tau are two injective homomorphisms of C into A and into B. So basically we say that the image in A is we amalgamate along this subgroup C. So we say that corresponding elements of subgroup C in A and in B are the same in this group. So
how do I understand this as a relation in terms of the generators S1 and S2, this S sigma C is tau C?
Sigma of C, okay, sigma of C is an element in A, right? So it can be written in terms of generators S1.
So I do this in any way because there are usually many ways. But okay, I see. Yeah.
I mean, somehow I'll give some examples now, but basically you just write sigma of C in generators S1, tau of C in generators S2. You can have infinitely many, like you can write it for every element of C, but sometimes it is not necessary to write it for every element of C. Sometimes it follows from like some other consideration. So for example, like let's talk about surface groups. Like let's take free product with amalgamation of two free groups. So one free group is given by generators A and B, another is given by generators C and D. And we amalgamate it along this cyclic subgroup C, generated by element gamma, and we define sigma of C as a commutator of AB and tau of C as a commutator of C and D. Like commutator is, I write commutator, it's A inverse, B inverse, I write it this way, AB. Okay, so, and now what are going to be the relations if we look at this thing? So S1, it is AB, right? S2, it is CD. So we have generators A, B, C, D. Now, and we only have one relation for this, because it is a cyclic group, right? So if we, every element is, so C is basically consists of powers of gamma, right? So it's enough to write that image of gamma in this group is the same as the image of gamma in this group. So basically we write relation AB equals CD, or we can write it this way, the product of commutators AB and DC equals to 1, right? And so it's a group, it is a orientable surface, a fundamental group of the orientable surface of genus 2. Like the fundamental group of the orientable surface of genus 2 is obtained this way. And generally, like if you have a, like, yeah, maybe before, no, maybe let me first go to surfaces. Actually, yeah, this is orientable surface of genus 2 represented as an amalgamated product, right, in my example. But we can do it like for any, like it is a topological, there is a topological interpretation of this construction of amalgamated product. Like if we have, so for any group, there is a connected CW complex, which is called Eilenberg-MacLane space. Like we can construct this complex like this. So these are generators, so we just take loops for generators, and then we glue relators. Like we take faces with a boundary corresponding to relators and glue each relator to this, glue each relator to here, right? For example, if this is A and this is B, and we have like the commutator A inverse B inverse AB, then we take this square labeled by A, B, no, A inverse B inverse AB. We take the square and just glue it here, like so. Glue it like A inverse B inverse A B. And we get a 2 complex. So we can do it for, and then this group, the group G is a fundamental group of this complex. So what we can do, we can take a Eilenberg-MacLane space for the group, for one group A. We can take it for group B, like let's denote, so we now have topological space X and Y, and then take it for the group C. So there are 3 spaces, and then we can realize sigma and tau as like mapping Z into X and Z into Y. Now what we can do, now we can take the disjoint union of X, Z, and cylinder, like here it's the direct product of Z and unit interval and Y, and take the quotient over this equivalence relation. Let me just show it here. So it's basically how I'm constructing this surface. This is my space X, this is my space Y. Like Z was a cyclic group, so it's a fundamental group of a loop. Direct product with a unit interval, so I got a cylinder. And then now I just glue this cylinder to X and to Y, because Z is embedded here and Z is embedded into Y. So I just glue them together and I get like this surface. Any questions? So it's basically like I can generalize this. Like if you take any connected surface, and we take gamma to be a separating simple closed curve, like something like this. I can take any surface, not necessarily of genus 2, and take a separating simple closed curve, right? Then the fundamental group of this surface can be obtained as an amalgamated product of the fundamental group of this subsurface and fundamental group of this subsurface amalgamated over a cyclic subgroup. So it's amalgamated product appears like this. This is an example how amalgamated product appears. Like later on, I'll show, this is actually what Searle proved, that SL2Z, special linear group SL2Z, is an amalgamated product of Z4, so cyclic group of order 4, cyclic group of order 6, amalgamated over a cyclic group of order 2. But this is going to be like a very nice construction, like to this proof, because this is not kind of obvious at all. So this is amalgamated product. And again, like one of the general examples is a connected surface, amalgamated, like two connected surface and separating simple closed curve. Then the fundamental group of the surface is an amalgamated product along this cyclic group corresponding to this curve. This is one construction which is again very important in Bass-Searle theory. So the another construction is a construction, and I'll talk more about amalgamated products because like what I'm going to do, like I'm going to kind of run Bass-Searle theory on the example of amalgamated product. Like I'm going to do proof by example. But there is another example, another construction, which is called H&N extension. So it's Higman-Neumann-Neumann extension. Like if we start talking about surfaces, imagine that we have a surface again. We have a surface again. And we take a non-separating simple closed curve, something here. We take a non-separating simple closed curve. Then the fundamental group of the surface is going to be like we can cut the surface along this simple closed curve. we got a topological space, and which has like a fundamental group, which is actually going to be a free group, and then we just take what's called H&N extension along this cyclic group corresponding to the simple closed curve, and we have a fundamental group of the surface. So it's another construction, which I'll talk more about it. So now we would like to know more about amalgamated products. So we need some results. Basically, like if we consider amalgamated products together with H&N extensions, and like if we can obtain the group, first taking amalgamated product like A1 and A2, then amalgamated product with A3, amalgamated product with A4, and so on. And then we take some H&N extensions of this group. Then the group which we obtain, it's called the fundamental group of graph of groups. And it is also the fundamental group of graph of spaces. Now, the word fundamental group maybe comes from like my examples on surfaces or in general in topological space, because actually amalgamated product, it is a fundamental group of some space, which is obtained by gluing together two spaces along like a subspace. So this is why the word fundamental group is used. And and such a thing, if you first take amalgamated products, then we take H&N extensions. This is called a fundamental group of graph of groups. And what Bass and Searle, what they actually proved, that it's actually Searle proved in his book Trees, and like Bass, whatever, they wrote much more general proofs together with Simon Bass. They proved that a finitely generated group acts on a tree non-trivially, if and only if it can be represented as a fundamental group of some graph of groups. And there is a much more information in like, this is called the main theorem of Bass-Searle theory. But it is quite technical theorem. So first what I'm going to do, I'm going to like talk more about amalgamated products, and I'm going to show that for every amalgamated product, I can construct a tree such that this group acts on this tree, and again, like more information. And also, in some cases, when a group acts on a tree, like with some additional conditions, we are getting that this group can be split as an amalgamated product. So let's just, it's going to be some bit of technical things, but I think it's probably necessary to do this. So suppose we have an amalgamated product of A and B. So we write A with generators and relations, B takes their free product, and then add relations that like, so C is now considered, yes, C is now considered as a subgroup of A. So instead of sigma and tau, we have like A and phi of A, which is B. So B is, which is, no, it's not A, it's C, and this is D. So we consider C as a subgroup of A, and phi of C as a subgroup of B. And now choose a system of right coset representatives. We call it TC, right coset representatives for C, and TD for D. Now, right coset representatives, so we represent like A is the union of C AIs, and B is the union of D BIs, right? So AIs are like this set of AIs. is TC. So it's a set of right coset representatives for C in A and for D in B. And then we say that like that a normal form, a C normal form in the group G is a sequence x naught, x1, and so on, xn, such that x naught belongs to C, xi belongs to, this is transversal, letter T stays for transversal. So it's a set of right coset representatives is called a right transversal of C in A. So xi belongs to C transversal in A and or xi belongs to D transversal in B, and the consecutive terms xi and xi plus 1 lie in distinct system of representatives. So like if x1 belongs to TC, then x2 belongs to TD. Similarly, we can define a D normal form. It will start with an element in D, but like elements from D in this group, they are equal to elements of C. So this is a C normal form. And the result is that if you have an amalgamated product, then amalgamated product can be uniquely written in the as a product G of these elements X, where this is a C normal form. So there are like amalgamated products are good because they have nice normal forms. Like free product of two groups have very nice normal forms, right? Like, I mean, we can just elements alternate, like element from one group, element from the other group, from one group, from the other group, and like two such representations, like such representation uniquely determine an element of the free product of groups. And actually, free product can be considered as a special case of an amalgamated product, right? If this group C is trivial. Like if the group C is trivial, then we just get a free product of A and B. But if C is non-trivial, still there is a normal form, and like every element can be uniquely written in this normal form. Now let me do the proof of this. By the way, this was invented, I think, certainly not before CERN, like the existence of normal forms and amalgamated products and H&N extensions. This was used by Higman and by Boone in different constructions. For example, in the construction of a group with undecidable word problem. So like, sorry, let me just. Okay. So this was used like long before CERN. Okay, so what we want to show that there is a unique normal form like this. Okay, so first of all, we have to show that we can take any element into a normal form. Now, every element, take arbitrary element G. If G belongs to C, then this is just, G is just x0, which is a normal form itself. Now, if G does not belong to C, then G is an alternating product of elements from A and elements from B, right? And suppose it does not belong to C. So it just alternates. Suppose it has this form. And then we'll show it, we'll do the proof by induction on the number of syllables in this form. Like one syllable, let me just do one step and it will take care of the induction. So, okay, so none of this, like AI and BI, they do not belong to C. None of them belongs to C. Because if, we can assume this, because if one of them belongs to C, like for example, if A belongs to C, A1, then it also belongs to D, right? And then element from D times element from B, it is also element from B because D belongs to B. So then I can just make this product shorter and use induction. So we already we assume that none of this, not AI, not BI belongs to C, and none of them belongs to, therefore none of them belongs to D. So also each element B in B can be represented as a product of elements from D and some representative of the right transversal, right? I mean, this because the whole group B is a union of, so the whole group B is a union of right cosets of D. And therefore, this is not the same I as here. And therefore, every element is B can be written as B tilde, which lives in D, and B bar, which is element, right coset representative, which belongs to this fixed transverse. Okay, so and then B tilde is was it sigma? I think I had 5. So whatever, like it's, I think I can mix the letter here, but B tilde corresponds to element A tilde, which is in C. Okay, so then let me rewrite my G this way. So it's A1, everything here not changed. And then instead of BK, I write B tilde times B bar K, where B bar, it is element from the transversal. And BK belongs to D. And therefore, it also belongs to C. It is equal to element which belongs to C in the group. And then I can join it with this element AK, denoted by AK prime. And then, so what I have this is element B bar, element from the transversal. And this product is shorter, right? And then I can apply induction to this product, bring it to the normal form. And the product of the normal form for A1, B1, and so on, AK prime, times element from the transversal TB, it is also a normal form. So that's a proof that that there is a norm, that every element can be written in the normal form. Now the second, now we have to prove the uniqueness, which I kind of at least hint how to prove it. So we are going to make our group G, which is an amalgamated product, act on the set of normal forms. So in the set of C normal forms. And actually, first we make A act on the set of normal forms, C normal forms. So if we have a normal form, now take element G, G is just in A. Take element G in A. So now, if this tau, if this normal form, if it is just element in C, if you just have x0, then G tau, it is Gx0. If G belongs to C, it is element in C. If G does not belong to C, then it is a product of element from C times the element from the transversal. Now, if tau does not belong to C, then we basically, then we just do the natural thing. We take a product of G and this element. Like, let me consider just one case. For example, suppose G belongs to C. Then we have this normal form, G times x0. It is element in C, so it's again normal form. And otherwise, we just multiply and bring it to the normal form. So we define this natural action of A on the set of C normal forms. Then we define the action of B on the set of D normal forms. And then, but then if B acts on the set of D normal forms, it also, there is a like one-to-one correspondence between the set of C normal forms and D normal forms. So then B also acts on the set of C normal forms, like this. And then if A acts on the set of the C normal forms and B acts, then their free product also acts. And then it is easy to check then these elements, C times element from C times the inverse of corresponding element from D, that they belong to the kernel of the section. If you just look at the definition of the action, which is completely natural. And therefore, amalgamated product acts on this set of C normal forms. And now we take some element G in G, and the action of G on the identity element, it is a normal form of G, but it is a unique, like the amalgamated product acts. So identity is taken to the unique element. and therefore normal form is unique. And so basically what we proved, let me just go back. We proved that, we proved the theorem that that every element can be uniquely written, every element of the amalgamated product can be uniquely written as in the normal form. Okay, now then, okay, then we are going to use it. So basically, like now we want to prove the following theorem. So a connected graph which consists of two vertices and two mutually inverse edges, basically two vertices and then edge. This is called a segment because we read edge in two directions, so this is why I'm talking about two edges, two mutually inverse edges. So it is a segment. Okay, so the first theorem. If we have an amalgamated product, then there exists a 3x on which this group acts without inversion on edges, such that the factor graph. Okay, what is the factor graph? If the group acts on some, what we're stating, that the group acts on some tree. What is the factor graph? The factor graph over the action, it is a graph of orbits, right? So it's a graph of orbits of vertices of the tree. So again, so if the group is an amalgamated product, then it acts on a tree without inversion on edges, and the factor graph, so the graph of orbits, it is a segment. Moreover, like this segment can be lifted into a segment in X, in the tree, with the property that the stabilizers in G of its vertices and edges are equal to G1, G2, and A, respectively. So basically, like what we say is that if the group is an amalgamated product, it acts on, then it acts on a tree, and there is some segment in this tree, like the tree maybe like this, and there is some segment in this tree. Then if you take a, like call it P and Q, that if you take a stabilizer of this vertex, and if you take a stabilizer of this vertex, and we take a stabilizer of the H, then G is actually isomorphic to GP, GQ, amalgamated product of GP, GQ over GE. Any questions? So the kind of the statement is that if you have an amalgamated product, then this group acts on a tree. And we actually know more. We know that it is, the group is actually amalgamated product of the stabilizer. There is some segment in this tree, so that the group is an amalgamated product of the stabilizer of one vertex in this segment, second vertex over the stabilizer of the H. Okay. Now the proof, I don't have too much time. Let me just basically just say, how do we construct this tree? The vertices of the tree is going to be the union of left cosets of G1 and G2. So the vertices consist of two classes: union of left cosets of G1 and left cosets of G2. Now we the edges are union of left cosets of A, like we had G1 over A with G2. So this was our group G. So vertices are left cosets of G1, union left cosets of G2, edges left cosets of A. Now sigma of GA is G, like this is the left coset. So sigma of GA, it is just GG1. Tau of GA, it is just GG2, like with the same representative. And T tilde is a segment with the vertices G1, G2. And positively oriented HA. And so the group acts by left multiplication on this tree. Like if we take element G, so if we have vertex G, G1, take element G1, so it takes G1 into G1, G1. So the group left by X by left multiplication. So that's a tree. Now this is a proof, but maybe like I talk a little bit about this next time. And then the result in the other direction, that if the group acts without inversions on edges on the tree, and suppose that the factor graph, so the graph of orbits, is a segment, then this group is isomorphic to the amalgamated product, and there is some, we can leave this segment in the tree, as I said, so we can leave this segment in the tree, and so then our group is an amalgamated product of the stabilizers of the vertices of the lift of the segment. So that's probably like skip the proof for now. Basically, so basically what we've shown that this is going to be next time, but what we have shown, we've shown that if the group is an amalgamated product, it acts on the tree, and we know how to construct this tree from the representation of group as an amalgamated product. Also, if the group acts on a tree and the factor graph is a segment, then the group is an amalgamated product. Now, the actual like Basseur's theorem says that if the group not necessarily amalgamated product, but obtained by amalgamated product and H&N extensions from its subgroups, then it acts on a tree. And if the group acts on a tree, then it can be obtained as a iterating the construction of amalgamated products and H&N extensions from the stabilizers, basically, of vertices of this tree. And so that's probably going to be already next time. But like next time, I also would like to consider an example, like SL2Z, so special linear group of 2 by 2 matrices, and we will show that like this was the goal of Searle, like in his book, one of the goals, to show that this group is splittable, that it splits as an amalgamated product. And he did show this by constructing the tree such that this group acts on the tree. And as a result, like again, like I'll do this next time, but as a result, so we can prove that SL2Z is an amalgamated product of cyclic group of order 4, cyclic group of order 6, over cyclic group of order 2. Okay, I think that's all for today. Thank you.
Well, let us thank Olga for the wonderful lecture. And are there any questions? I didn't see any in the chat, but now is a chance to ask. Any questions?
That's a very nice classical theory.
It is, yeah, it is.
Very elegant and reputed, well reputed.
It's
Thank you very much.
Basically, I mean, like it's kind of, it all goes back to Felix Klein, right? So what if we have a group acting on some space or some model, right? What can we say about the group? And also, like, if you say something about the group, where it can act by automorphisms. So it's basically Butts and Searle, they answered completely the question, like if a finitely generated group acts on a tree, what is the construction of this group? And the group is splittable then. like S amalgamated products and H&N extensions.
This connection with topological spaces and group theory is very remarkable. I remember old days when the theorem of subgroups of free amalgamated products was proven by Kurosh years ago and by purely combinatorial methods. But if you translate it into the language of the spaces, then it becomes just two lines.
Yeah, it's
Much
like, for
shorter proof.
example, like the result that a subgroup of a free group is free, right?
Yeah, yeah.
Like, I mean, it will be very complicated combinatorial proof, like Schreier's, whatever.
Nielsen Schreier. Yeah.
And if like basically free group is a fundamental group of a graph, right? And a subgroup of it is also a fundamental group of a graph, of the cover, of
Yeah.
this, which is also a graph, so it is free.
Yeah.
It's
But same true also for the amalgamated products as well, subgroups of amalgamated products. So that's a hell of calculations by hand if you do it only with elements and generators and relations. But once translated into geometry, that produces a miracle.